We're going to talk about Taylor polynomials today. If we start with the function f of x with the Taylor series, this should be series, given by this. The Taylor series for f of x is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared, etc. Remember, the kth Taylor coefficient, that's the coefficient on the x minus a to the kth power, is exactly the kth derivative of f at a divided by k factorial. So remember, we can think of f of a as the 0th derivative of f over 0 factorial. 0 factorial we interpret as just 1. And f prime of a we can think of as the first derivative of f over 1 factorial. And then, of course, we have the second derivative of f at a over 2 factorial, etc. This is the general form of a Taylor series for a function f centered at a. That's the Taylor series. What do we mean by the nth degree Taylor polynomial? Well, what we mean is just a partial sum of this Taylor series, the first n terms of the Taylor series. When I say first n terms, I mean go all the way out to the nth order term. So if you include the 0th term, that would be n plus 1 terms. The nth degree Taylor polynomial is just the sum from k equals 0 to n of this kth Taylor coefficient, the kth derivative of f at a over k factorial, times x minus a to the k. That would be f of a plus f prime of a times the quantity x minus a plus f double prime of a over 2 factorial times x minus a squared, plus etc. But then we have a last term, which is the nth derivative of f at a over n factorial times x minus a to the nth. You can see this is an honest to goodness nth degree polynomial. Now, what are Taylor polynomials about? Well, under nice circumstances, and this will hold for many functions, the original function f will actually equal the Taylor series, at least for x in some interval centered at a. That interval will often be an interval with whose radius is the radius of convergence of this Taylor series. There are many examples of Taylor series, which we'll be talking about soon, which are where the function is equal to the Taylor series on the entire real line. In other words, they would have radius of convergence infinity, and the function is equal to the Taylor series everywhere. Now, this Taylor series is not a polynomial. We can kind of think of it like an infinite polynomial, but it's not a polynomial. It's a series, and we have to treat it as such. The nth degree Taylor polynomials are honest to goodness polynomials. They're what we get if we cut off the Taylor series after the nth degree term. So we're ignoring the rest of the Taylor series that would keep going and going. This nth degree Taylor polynomial is not equal to the original function f in general, assuming f wasn't a polynomial to begin with. But it will be what we think of as a polynomial approximation to f. Here's an example. The function e to the x, very simple but very important function, has this as its Taylor series. And I'll remind you the reason. You saw this in the video lectures from the previous day. If f of x is e to the x, f prime of x is also e to the x, f double prime of x is also e to the x, and they're always e to the x when you take more and more derivatives. So what are these Taylor coefficients? The kth Taylor coefficient is just the kth derivative of f. In this case, at 0, this will be the Taylor series centered at 0, divided by k factorial. But if all these derivatives are always e to the x, when we plug in 0, we get 1, so this is just 1 over k factorial. So you see the coefficients here is 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, etc. It's easy to use the ratio test and see that this series converges for all real x. In other words, if you use the ratio test, you can see that the radius of convergence for this Taylor series, for this power series, the Taylor series for e to the x, is infinite. And in fact, we can show, we'll talk about this a little later, that e to the x is really equal to the value you get from this series for every real number x. What can we say about the Taylor polynomials? Well, we can start with T0 of x. That's the 0th degree Taylor polynomial. That's just what you get when you take only the 0th order term. That's the constant function 1. Here I've shown you the graph of our function f of x equals e to the x. It might be hard to see this, but for e to the x, it's the black line, which you can see a little bit of here, but then it gets kind of stuck in with the other colored lines. So the graph of e to the x goes up here like this, but the constant function 1 is just this constant here. That's the 0th degree Taylor polynomial. The idea behind the Taylor polynomials is often that they're an approximation for your original function, in this case e to the x, and that approximation should be good near the center of the series. Here we have a series centered at 0. If you look just near 0, what constant function best approximates e to the x? Well, the answer, of course, is 1, because e to the 0 is 1. And if you're only interested in values close to 0, that's the best approximation you're going to get with just a constant. T1 of x, the first degree Taylor polynomial, is what you get when you take, in this case, the first 2 terms up to the first degree term in the Taylor series. So you'll just get 1 plus x. If we graph T1, you'll see you get this line, y equals 1 plus x. It's this perfectly straight line here. And again, near x equals 0, this will be the best linear approximation to the graph here, y equals e to the x. You can remember, you can barely see y equals e to the x. It's this black line here that follows that upward trajectory. In fact, this first degree Taylor polynomial, the graph of that first degree Taylor polynomial is just the tangent line to the graph of e to the x at the point 0, 1. And you already should understand that this tangent line should be a good approximation to the graph, at least near that point of tangency. How can you get a better approximation to the graph of e to the x near that same point 0, 1? Well, if we look at the second degree Taylor polynomial, that just means take the first 3 terms up to, that means up to the second degree term here. 1 plus x squared over 2. That's what you get here. I believe that's the green line, the green curve here. That's a quadratic function. This green curve, you can see, has the shape of a parabola. And near the point 0, 1, that green curve, the parabola, is a better approximation to e to the x than just that straight line. And you see how it hugs really close to the graph of e to the x over a longer range than just that line does. How can we do better? Well, we take another term. We can look at the third degree Taylor polynomial, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. A beautiful third degree polynomial. The graph of that is the red line here, and you see it hugs the graph of the exponential function over a wider region than even the second degree Taylor polynomial. But you notice that if you go far away from this point 0, 1, you take x's that are away from 0. 0 is the center of the series there. If you go far away, the second degree Taylor polynomial goes way up like that. The third degree Taylor polynomial goes way down like that, whereas the actual exponential function just tends to 0. In other words, these polynomials are very good approximations near this point of tangency, near the point 0, 1, where x is 0 at the center of the series, but they're very bad approximations if you go very far away from that point. We could keep going to the, well, there's the third degree Taylor polynomial. We could go to the fourth degree Taylor polynomial or the fifth degree Taylor polynomial. I just wrote down here the sixth degree Taylor polynomial is what you get when you add up the terms all the way up to the sixth degree one. Here, this purple line, which you can barely see here, the purple line starts to hug really close to the black line, the actual graph of e to the x, beginning around here, and it stays really close. Basically, the black line and the purple line overlap for the rest of this picture. The difference between the two is so tiny that it's less than a pixel when you get just a little bit past -2 here, going all the way up here to the right, as far as you can see. E to the x is very different from the sixth degree polynomial if we were going to go way far to the right or way far to the left, but over a reasonable interval here from about -1.5 to 1.5, the two are amazingly close. How can you get a function, a polynomial that's close to e to the x over a much larger region? Just take higher degree Taylor polynomials. Let's look at the cosine function. The Taylor series for the cosine function, and when I say Taylor series, these are Maclaurin series, which just means the Taylor series centered at 0. Is given by this. The reason for that is when f of x is cosine x, you all know that f prime of x is minus sine x, f double prime of x is minus cosine x, f triple prime of x is sine x, and then it keeps going. The fourth derivative of f at x is back to cosine x, and it keeps going. When we plug in 0, the center of the series, these alternate from 1, 0, negative 1, 0, 1, 0, negative 1, 0, etc. So we look at the Taylor coefficients, which are the kth Taylor coefficient is exactly the kth derivative of f at 0 over k factorial. That will alternate between 1 over k factorial, like this 1. Then you'll have 0, so that term looks like it's missing. Then negative 1, in this case negative 1 over 2 factorial. The next one would be 0, then you'll have a positive 1, now over 4 factorial, then 0, then a negative 1 over 6 factorial, then 0, etc. This is the series for cosine, and just like the series for the exponential function, this series converges for all real x. The radius of convergence is infinite, and it's equal to cosine x for every value of x. The graph of the cosine function, just like before, is given by this black line here, y equals cosine x. You can see it just goes up and down and up and down. If you continued, it would just be a standard looking wave function here. Cosine of 0 is 1, so it goes to this point 0, 1. Just as before, t0, the 0th degree Taylor approximation, is just the constant 1. You can see that right at this point, 0, 1, the best 0th order approximation, which would mean a constant approximation to the cosine function, is that horizontal line, which in this case is the tangent line. But now notice something interesting, that it is the tangent line because t1 of x is the exact same as t0 of x. It's just 1. If we take the Taylor series up until the first degree term, well, the first degree term is 0, so we just have the same thing 1. So this 0th order approximation is the same as the first order approximation. The second order approximation, the second degree Taylor polynomial, t2 of x is 1 minus x squared over 2. That's the green line here, or the green curve, I should say. And you see that's a parabola, in this case opening downward. And you see that's a really good approximation for the cosine function on some reasonable area from here to here. It's an amazingly good approximation. You can barely tell the difference in the red pixels and the green pixels. But then it starts to diverge and get to be worse and worse as you move further and further away from the center of the power series. Notice that t3 of x, the third degree Taylor polynomial, is exactly the same as t2, again because the coefficient on x cubed is 0. So you don't get anything better by doing a third degree Taylor polynomial than you do here by doing a second degree Taylor polynomial, just because that third degree term has a 0 as a coefficient. The fourth degree Taylor polynomial I have drawn here in red. This is y equals t4 of x, this polynomial here. And you can see it has the shape of a typical quartic, this kind of W shape. It's a very good approximation to the cosine function on this wider range than the second or third degree Taylor polynomials, which were both the same, the green one here. But it starts to get far away from the correct thing if you go out past, say, -2 or past 2 to the right there. And then I've shown you here t5, of course, is the same as t4. t6 I show you in the purple curve. It's a very strange looking curve, but it hugs extremely close to the cosine function over a wider region. And if you just continued with higher and higher degree Taylor polynomials, you would find polynomial functions whose graph really hug the graph of the cosine function over larger and larger ranges.